Thank you, Dr. Navid, for the insightful presentation today. And also, I would like to thank Mr. Ong and Mr. Sabir, who is also joining us today for this Q&A session. So there are a couple of queries on nonlinear modeling. And since we have Mr. Ong and Mr. Sabir, so I will try to divide some questions to them as well. So first, I want to start with one question regarding your slide that you presented, Dr. Navid. So it will be for you. So there is one query that the participants want more clarification on the slide where you were showing the graph for the wind load level and the design level forces. So in that one, does this mean that a service or strength wind doesn't push a structure to a nonlinear range like it does for the earthquake?
That is the assumption, and that is how because wind level, as you know, is the surface wind level is about 60%, is normally kept at 60% because the wind factor is about 1.6. Actually, it will be slightly less when you combine it with dead load and live load, but it is still kept below the nonlinear yielding. So it is assumed that the wind surface wind will definitely be below the yielding of any of the members. And some cracking is expected, but it's not assumed that any nonlinearity beyond the initial cracking will be activated. Unless now that we are talking about long duration winds like 1,700 return period, where some nonlinearity is being allowed using in the wind PBD documents, but not in the traditional codes yet. And maybe Ong can add later when he speaks.
So before moving to other colleague, I want to add one more question to you. So it's about the bridge concrete pier with the shape of the wall type for the wall type pier. So there are three questions on that. So I'll try to go step by step. So the first question is, how best can we choose a backbone curve or the FD relationship for that kind of concrete pier with the shape of the wall type?
Yeah, so as I mentioned to you just now, if it is a wall type and it's because bridges are slightly different from building because the direction of their response is very clear along 1 and 2 axes, inclined axis, unlike in building where things can happen in any direction. So either the wall will be bending along the bridge, which will be about its minor axis, or it will be deforming across the bridge, which will be perpendicular to the bridge axis. So if the wall you are expecting the bridge pier to deform across the bridge axis, which is perpendicular to that one, then it's not really behaving as a column, and it should more properly be modeled as a shell or as a fiber section. But if you're expecting the wall to deform along the bridge axis, in that case, you can just represent it by a typical PMM hinge also, because axial load normally is not that large. So depending upon the available tools and depending upon the primary interest of the pushover or primary interest of the earthquake, the pier can be modeled both as a fiber section or as a wide column hinge, which I described earlier. So backbones will come in a similar manner. Normally ASC backbones may not work, so AASHTO has its separate guidelines, and they can also be derived directly from the moment curvature of the cross section itself with modification for degradation.
Okay, so moving forward for the second part of the same question. So are there any testing data available for such large sections?
Yeah, once again, like I mentioned, the section size effects are, if the section size itself is not the issue, it's the proportion with the overall size, the dimension of the member. So even a wall, maybe 20 meter in section, but very high, let's say 50 meter, is just a column with a section. So it's the ratio of the structure's geometry to the cross section. But if it's a short wall, like for example, the height is very small and the section is long, then it's no longer a flexural member. Then shear will govern, and all this hinging will not really work. So we are talking about members which are governed primarily by flexural deformation, where such nonlinearities should be used. For members which are deep and shear behavior governs, then none of these hinges will really work very well. And then in that case, probably the nonlinear shell element might work.
I think that also explain the last part of this question. So moving forward, I want to go with Mr. Long. So there is a question about the slab. So does the two-way slab also have a shear plastic hinges at the mid-span when subjected to the uniform distributed load?
Normally, we do not allow the nonlinearity in the two-way slabs under gravity loads. For the two-way slabs, when we consider the nonlinearity, we consider under the earthquake loading. So we consider the nonlinearity due to fracture yielding of the slab at the near the column connection or the wall connection. So uh, important one is the ductility of the slab. It depends on the punching shear capacity of the slab, especially at the column location. So if you have the larger punching shear capacity margin and the gravity loads, so you will have the good ductilities. In ASE 41, they have the nonlinear post deformation relationship for the two-way slabs, especially for the flat slabs. You can
Thank you.
model that as an equivalent beam and provide the moment hinges at the ends of the beams.
Nice. So moving forward, there is one more question regarding to the shear wall nonlinear hinges on ETAPS. So I would like you to give some insight on that one too.
Yes, shear wall nonlinear modeling in ETAPS, there are two ways, as Dr. Naveed presented. One is the layer shell modeling, and another one is the fiber modeling. So we can model the flexure behavior, axial flexure behavior of the walls using fiber model or layer shell model. For if you use the fiber model, you have to model both modeling approach. You have to define the material stress strain relationship, nonlinear relationship in material level. But for fiber model, you can discretize the shear wall element with the fiber elements number of fibers. If you use the layer shell, you have to discretize the wall using make the mesh finer mesh in the shell elements in the wall, or you have to discretize the wall using large number of integration points. So there are two ways in the layer shell, but it is not good if you use layer shell with a very large shell element, one panel to represent the 8-meter length wall with the 3-meter height, and use the default integration point. I think it is only 2 integration points, so it will not discretize the wall properly, and it looks like you're modeling the wall with the 2 fibers only with a big wall. So it is better to consider the discretization properly in the walls.
So before I move to Mr. Sabir, I want to take one question for Dr. Naveed. So it's about the precast wall panels. And the question goes like, what is the best way to model gaps between precast wall panels?
Yeah. So as I mentioned, the gaps kind of behavior is best modeled by links, nonlinear links. So you can use a gap element. So where you can basically model the gap and the opening and closing of the gap and the force transfer between the gaps either way by whichever mechanism. So we can include friction, we can include the separation, we can include the shear, many shear keys. So very complex behavior between precast panels or even bricks, for example, can be modeled by using appropriate nonlinear links, but they have to be placed, properly, distributed properly, and with appropriate properties. So I think it's possible, but we need a little bit more understanding of what we are trying to model.
Thank you. So with this, I also would like to invite Mr. Sabir and would like to ask one question for him. So from what I understand from the nonlinearity is applied to the specific elements, not all the structure at once. If so, how can we pick the structural elements that will fail first? Is there any path to that? Would you like to give your opinion?
Yeah, so basically, but normally when we are doing the nonlinear building models, what we are doing is that we are modeling flexural nonlinearity in structural component that we think that will change the behavior of the structure. So say for example, walls and columns, those are the gravity load carrying elements. So we will model the nonlinearity in that. And coupling beams, and because coupling beams join the core wall together, so failure of a coupling beam can actually make our structure very flexible. So we have to model the nonlinearity in that, and also the girders that are connecting to the columns as well, because those are the elements when they yield, basically they are going to change the behavior of the structure. So it's important to model nonlinearity in that. As Dr. Naveed mentioned earlier, also in case where we have um, infill walls as well, and especially if they are connecting column to column, and we feel like the failure of the infill wall can suddenly put a lot of stress on the column. So in that case, we should look to model the infill walls as well. So usually, whenever we are trying to model nonlinearity in a structure, we are only looking to model nonlinearity on the elements which we think will uh, change the behavior of the structure. Let's say, for example, if you were to remove that element, what will happen to the modal properties of the structure? And if the modal properties change significantly because you had removed that structure, then you should model nonlinearity in that element.
I want to add a few things. In performance-based assessment guidelines, like ASCE 41 or tall building design guidelines like LADPSTC. So we have to classify the actions first. We have to consider, we have to classify force control actions or deformation control actions. So if we want to classify that action, a particular action as a deformation control actions, we can model, we model as a nonlinear behavior. If we classify as a force control action, we model as a linear behavior and check the strength capacity. So for the force control actions, we normally use uh, the actions which are brittle behavior, like the shear response of the beam, shear response of the walls, or some important members that we would like to remain elastic. For example, foundation flexure capacity. So we would like to remain elastic, or we consider the transfer beam, transfer girder, flexure capacity as elastic. So we will consider as force control action. So we have to model those actions as a force elastic and get the force demand and compare with check with the strength capacity. Sometimes if people wants to model the limited nonlinearity in their model, for example, in the building with the core wall, they want to allow yielding at the base of the wall and let the wall upper part to remain elastic. In that case, they can model, but upper part of the wall, whatever the force demand, moment demand resulting, you have to check with the strength capacity so that the upper part of the wall remain elastic.
Thank you. There is one more question I would like to have opinion from Mr. Sabir, that how can we model the hinge of a pre-stressed girder in a bridge?
Yeah, so usually if you look at the modeling guidelines, right, usually when we do the nonlinear modeling for buildings, we follow ASCE 41, and they have the modeling parameters available and also the acceptance criteria for typical elements, but they do not say anything on the pre-stress element. But if you are talking about the pre-stress element for bridges, then I think the guideline that will serve well is the Caltrans seismic guidelines, because Caltrans seismic guidelines, actually what they do is that they do not have a comprehensive force deformation curve as you get in ASE 41, but what they do is that they allow you to use moment curvatures, but the moment curvatures are basically limited, so you cannot just like have ultimate ductility or whatever like that. So they will ask you to check whether you have reached your concrete crushing strain first or the strain in the tendons first, like that. And then using those guidelines, you can you can develop a moment curvature relationship. And also Caltrans also provides the guideline how to calculate the hinge length of the girder as well. So you can multiply the hinge length with the curvature, and with that you can get basically a post deformation relationship or between moment and rotation. It will not be as comprehensive as you get in ASE 41, which tells you what is your ultimate rotation and where do you have strength loss and stuff like that. But it can be like a good basically elastic perfectly plastic backbone curve for you, which you can use for girders in bridges, pre-stressed girders in bridges.
Thank you. So there is one question regarding to some software uses. So I would like to request either Dr. Naveed or Mr. Long can take this question. It's kind of a general thing. So what informations are required by the program to introduce the boundary nonlinearity? Example, soil structure interaction. Generally that we use in the software.
Yeah, so maybe I can take some of them and then On can add later. So soil structure interaction is actually a subject which is very uh, complex in the sense that we are trying to model two very different materials with very different stiffness response which are joined together. And the soil varies so much from rock all the way to very soft clay. So that means that the variation on the soil side is very large. So now the nonlinearity response between the structure, whether we should include soil or not, depends on the relative stiffness of the soil and the structure. So some buildings which are flexible by itself, their response may not be affected by the soil structure interaction. But some structures which are rigid and the soil is soft, then their response will be affected. So we have to see a little bit about what kind of structure is on what kind of soil to start with. Once we go into the interaction, obviously the minimum level is you put springs on it. So you present the soil by equivalent springs, which are linear. And that is the absolute minimum that we can and we should do in most of the cases. Just replace the soil by equivalent springs around the structure represented by its stiffness modulus. But if the soil behavior is expected to be nonlinear or is very soft, then we can convert that into PY curve, which is like the nonlinear response of the soil's deformation with the pressure over the axial load. And then we can put those as nonlinear links against the structure. So that means that we are converting the soil response and attaching them by springs. But now the springs are no longer linear springs, but rather nonlinear links, capturing the soil force deformation relationship. So that's the second level. The very advanced level is where you use programs like Plexus that actually model the soil, real true nonlinearity, and then bring it back to the structure, which is very hard, but can be done in extreme cases of very, very structures which require this kind of analysis, like nuclear power plants or something like that, or underground structures. So maybe On can add a little bit on that.
Yes, sir. So the first one is the building is pushing the soil, and we model the soils as a spring to restrain the building basement. So because of the building movement, the soil springs will be activated and it will push the retaining wall. That one you can consider depending upon the type of the flexibility of the building, and also you may consider the nonlinearity in the soil. For the tension side, you ignore the soil stiffness in the nonlinear properties and consider the soil effect. Another one is second part is as Dr. Naveed mentioned, very complicated one. That one is considering the damping effect of the soil as well as the inertial force due to the soil itself. Because of the surrounding soil mass, it will also have the acceleration and it will generate the inertial force and push to the basement wall. So that effect will be more complicated if you consider in the analysis. But for the important structures, underground structures, you may consider it. Another part is another way is you simplify the model. So you do not model the soil structure interaction and do not restrain the basement with the soil, basement with the springs, but you ignore the mass of the basement in your finite element model. At the ground level, you consider full mass of the ground floor, but in the basement floors, you ignore the mass in the basement, and also you do not model the lateral soil springs. That one also you can consider in your analysis. Detailed procedures mentioned in Los Angeles tall building design guidelines. They normally considered a core footprint or tower footprint in the basement level mass.
So first I would like to go with Mr. Ong. So what's the good practice for modeling the coupling beams in ETABS or SAP 2000?
Okay, for linear analysis, you can model the coupling beams with the frame element or shell element. If the coupling beam is deep, you can model as a shell element to capture better stiffness. But for the nonlinear modeling, you better to model the coupling beam with the frame element and assign the moment hinges or shear hinge if you use the diagonal reinforced coupling beam. So for the nonlinear part, you better to model with the frame element.
So there is one question regarding the retrofitting, and I would like to get opinion from Mr. Sabir. If we integrate the retrofitting material into the nonlinear model of a building under investigation, do we need to assign the nonlinear properties of that retrofitting material, say the nonlinear properties of carbon fiber or steel plate?
Yeah, so that basically depends upon whether the action is a force controlled or a deformation controlled action. So if it is a force controlled action, which is usually modeled as linear, in that case, we do not need to update our nonlinear model. We can just simply take the demand and then check whether the additional, let's say, carbon fiber or steel plate, whether we are adding adds the enough capacity to be able to satisfy that demand. But if it is a deformation control action and we want to see that whether that deformation control where our deformation is enhanced, we can then try to maybe model the retrofitting but that will be only possible in case of fiber models where we can add, let's say, steel plates in the wall modeling to see whether that helps us with the deformations or not.
For example, if for retrofitting projects, existing building projects, first we have to create a nonlinear model without retrofit measures as existing and check the deficiencies. And then we decide the retrofit strategy and provide the retrofit measure. If in that case, we have to create another updated model, nonlinear model with the retrofit measures. If we add the global strengthening with the braces or whatever, we have to add. But for the local retrofit measures like column, if we strengthen the retrofit the column with the steel jacketing for the shear capacity requirement. In that case, shear capacity is a force control action. We may not need to model, update the model nonlinearity, but that shear jacket, that steel jacketing also improves the axial flexural capacity of the column itself. So we better to update the model PMM hinges with the steel plate properties as well, and then we run the nonlinear analysis.
So before we close, we would like to hear something about this, as there is a question that is there a way to integrate AI in CSI software like SAP 2000 and ETABS?
Yes, this is an interesting question. Of course, the AI, including in the software, there are so many places where we can do that before, during, and after. So that means one is that you integrate AI into how you create your structures or predict the behavior before even you model it. So that means AI is kind of a replacement for the finite element or the design process, because AI can predict something based on the previous experience, but that can be used for initial design, for other things. So that's a lot of work has been done in that area where you don't need to use the traditional software, at least to a certain level of response check or decision making. That is the predictive design that we are working on. So of course, that's one area. And we already have several software which we are, like for example, Bridge, we just finished the CSF Bridge Express, where the entire design of the bridge can be predicted beforehand because it's trained on 8,000 bridge models and so on. So, and then they can be verified by the program. So that's one part of AI, which is before you start the design, you get a good initial design because you need the initial good design to carry out with the rest one. Second one is that you put AI in the way that you use the program. For example, you have a conversation with the software rather than trying to find where data to input there. So less learning is required because software are so complex. There are thousands of forms, thousands of data. Finding the correct data to change is a major task where people have to spend a lot of time. So AI can help a conversational way to work with the program. Say, okay, just say change beam number 4 from this to that one. And that's where, once again, CSF Bridge Express and other programs already have that functionality where we can have that conversation with the program, reduces the learning, and also makes the changes easy. Next one, AI, is what we call the model explorer or the result explorer. That means you can have a conversation with the model, finding what is there. So AI can convert your queries, natural language queries, go into the model, find all the relationship, and give you the answer rather than you going through hundreds of tables to find a particular data. For example, say, tell me which beam has the maximum deflection for load, whatever. Then it goes there, gives you the results, and explains that. That is another level where AI can be used. Then we have AI where it can actually replace for example, a lot of work is being done on the prediction of the ground motions, for example, a lot of work over there, prediction of the PBD using AI. So AI is coming in many ways to include in various levels of workflow that engineers do. And obviously, CSI programs are now working towards that. And hopefully, we will see many of these very soon.
Thank you very much, Dr. Naveed. I would also like to extend my thanks to Mr. Ong and Mr. Sabir for joining today's session. And thank you all the participants for the wonderful participation. Also, I would like to announce that all the questions which are pending and that we could not take it today, we will try to respond to all of them soon, within maybe a week or so. So thank you very much.